Modern AI agents rely almost entirely on large language models that are inherently stateless. To give them a semblance of long-term memory, developers typically use standard vector RAG, an architecture where text is converted into mathematical vectors and mapped in high-dimensional space. When you ask a question, this system relies entirely on single-stage semantic similarity. It calculates the distance between the words in your prompt and the data chunks stored in its vector database, retrieving whatever sits closest. This mechanism treats stored information as an unlinked stack of pages. It identifies that two paragraphs contain similar vocabulary, but it ignores the structural, logical relationships connecting the facts inside them. That becomes a critical liability for complex reasoning. If you ask an agent to trace a modern supply chain, it has to follow a strict sequential path of suppliers, manufacturers, and distributors. Simply finding words that sound similar to your query fails to reconstruct that specific chain of events. We see this ambiguity clearly with overlapping terminology. If you are searching for Apple, standard vector spaces struggle to separate Apple the technology company from Apple the fruit. Both occupy nearby conceptual territory based purely on proximal terminology. When standard RAG hands this unordered, ambiguous data back to the LLM, the model lacks explicit instructions on how the pieces fit together. It is forced to probabilistically guess the connections between them. Relying solely on semantic proximity causes hallucinations in enterprise environments. The architecture lacks the relational logic required to verify exactly how two distinct pieces of information interact. Fixing this bottleneck requires a structural convergence, bringing together connectionist neural networks and symbolic rule-based logic. In the modern tech stack, symbolic AI takes the form of a knowledge graph. Instead of floating in abstract space, data is organized into explicit nodes representing entities and edges defining the specific relationships between them. Recent research into GraphRag from Microsoft and the AAAI validates this approach. By extracting structured entities from raw text, the system gives the LLM deterministic traversal paths. The ambiguity is resolved before the language model ever generates a response. This diagram from the research outlines the mechanics of GraphRag. Looking at the left column, during indexing time, unstructured text is broken into chunks and processed to extract specific entities and relationships, which form the base of the knowledge graph. Following the right column for query time, the system detects dense communities within that graph. This allows it to generate comprehensive answers drawn from structured community summaries, rather than returning fragmented lists of text chunks. This multi-stage reasoning engine mirrors how a human expert works. It deconstructs the query, consults a structured knowledge base, and synthesizes an answer. Building true agentic cognition means moving away from flat databases. Developers must adopt memory systems that natively merge semantic search with structured graph logic. SmartMemory is the engineered implementation of this hybrid theory, designed to give AI agents reliable, persistent recall. The system operates on a physical architecture called hybrid triple storage. It distributes incoming information across three parallel systems: a vector store, a graph database, and a metadata store. When raw text enters the system, it is converted into embeddings and sent to the vector store. This preserves the agent's ability to understand nuance and semantic similarity. Simultaneously, the system extracts entities and maps their explicit relationships into the graph database, locking in the structural logic. Finally, temporal data, user IDs, and tags are logged in the metadata store, establishing a timeline for strict time-based filtering. This architecture enables parallel querying. An agent can execute a search that asks, "What concepts feel similar to this problem?" and "What components are strictly connected to this problem?" at the same time. This tripartite routing provides the semantic flexibility of language models alongside the reliability of structured databases, without forcing a compromise between the two. Efficient data storage is only half the battle. If an agent retrieves every piece of connected data at once, it becomes overwhelmed by irrelevant context. SmartMemory solves this through cognitive partitioning. Incoming data is categorized into 5 functional memory types, mimicking human cognitive architecture. Working memory serves as the active, short-term conversational context. It handles the immediate problem-solving steps within a single session. Episodic memory logs sequential events and personal interactions. It acts as an autobiographical record tied to a specific user's timeline. Semantic memory acts as the repository for broad factual knowledge. This holds concepts, policies, and definitions that remain true regardless of the specific conversation. Procedural memory dictates how the agent should act. It stores behavioral templates, system prompts, and reusable workflows. By partitioning data by cognitive function, the system protects the LLM's limited token window. The agent only loads the specific cognitive domain required to execute the current task. As an enterprise dataset grows, traversing millions of individual nodes in a flat graph slows an agent's context processing speed. To maintain efficiency at scale, SmartMemory runs continuous background processes, specifically the hierarchical organization evolver. This algorithm actively analyzes memory clusters to detect natural groupings. It abstracts distinct concepts into a multi-level structure without requiring human-defined schemas. For example, it automatically groups individual technology nodes like CNNs and RNNs into a deep learning category, and then nests that under a master artificial intelligence node. This structure enables local search. An agent can enter the tree at a specific low-level entity node and fan out to find precise, granular data. It also enables global search. By querying the highest-level community summary nodes, the agent retrieves holistic answers to broad, thematic questions about the entire dataset. Unsupervised hierarchical clustering allows agents to shift between microfactual precision and macro-thematic reasoning, bypassing the processing limits of massive databases. The final requirement for advanced cognition is deep, cross-domain knowledge synthesis, the ability to think laterally across different subjects. SmartMemory achieves this through its fifth cognitive partition and native implementation of the Zettelkasten method for atomic knowledge management. The core mechanic isolates single ideas into atomic notes, assigning each a permanent identifier. The system automatically extracts entities and draws bidirectional semantic edges to existing notes. This happens in the background, independent of human tagging. This creates an emergent, self-organizing knowledge structure. As the web grows, the agent can traverse these edges to discover analogical connections between entirely different fields of study. The Zettelkasten protocol transforms isolated storage into a living web of associative pathways, allowing the agent to synthesize insights from disparate data points. Without maintenance, long-term AI knowledge bases inevitably degrade. They fill with redundant facts, isolated nodes, and contradictory information that pollutes the agent's context window. SmartMemory runs background evolution algorithms that continuously scan the graph for these inefficiencies. Through a process called memory consolidation, the system identifies and merges semantically overlapping facts, removing redundancy. It also performs strategic pruning and semantic decay. The system weakens or archives connections that are rarely accessed or out of date. This ensures the search space remains optimized. By mimicking human forgetting curves, the agent maintains focus on accurate, actionable data. By integrating symbolic knowledge graphs, vector semantics, and continuous autonomous evolution, SmartMemory transforms LLMs from stateless prediction engines into persistent architectures capable of verifiable reasoning that compounds as more data is ingested.